Not a huge number of people here. Let's see. How are you? All 5 of us. 6 with myself, right? So, yeah, we got a couple people watching. Man, crappy day today. It'll be worse tomorrow. It's like we're not even going to warm up. I heard someone mention, at least we're not getting snow. I guess they got snow up in Lubbock, maybe? Lubbock or Amarillo. Probably, definitely Amarillo. First snowfall is always the nice one. After that, and it gets old. All right, let's pick up. So predicting population sizes, population dynamics, we've described them. Described populations based on those 3 fundamental descriptors, right? Population size or density, spatial dispersion, and then we have our demographic characteristics. We're focused now on the dynamics. How does a population change? And we start off with the basics, which is just predicting a population size. What's the size after so many years or so many generations of reproduction? So we introduced at the start of this presentation the factors that primarily affect population size, which was births and deaths. All right, those are the 2 main factors, and then immigration and emigration. And as we get into these equations, we're going to assume that there is no net migration. So I minus E equals 0. A lot of our assumptions might say that it's a closed population, meaning no migration whatsoever, but that's the same exact idea as saying no net migration. As long as you have the same number of people or same number of individuals entering our populations as leave, we're going to be okay. All right? So I believe we left off on this slide, and we introduced these terms, discrete versus continuous and overlapping versus non-overlapping. We're going to break our equations down based on these characteristics of their generations. So discrete versus continuous really refers to when does reproduction occur in our population. All right? So if all of the reproduction occurs basically within a very small period of time, we're dealing with the discrete generation. We can very easily see when the cohort enters our population, and we can track that cohort from year to year to year to year. All right? In a continuous distribution or continuous generation, we don't have that synchronized births anymore. All right? Our reproduction could occur anytime during the year, which makes it difficult to try to track individual cohorts. Yes, we can arbitrarily define a cohort by saying all individuals born within this certain fixed amount of time, that's going to represent our one cohort, but we recognize that as soon as we get out of that one fixed period of time, reproduction starts again. All right, so it makes it difficult to identify those cohorts. So that's discrete versus continuous. Overlapping versus non-overlapping refers to reproduction of our adults and our offspring. So if we have non-overlapping generations, then all of our adults are going to die before their offspring start to reproduce. All right, annual plants, I said, was a great example. Annual plants are discrete. You can identify the cohort very easily. They have non-overlapping generations. If you have overlapping generations, then our adults are going to multiply or reproduce multiple times, including reproducing when their offspring start to reproduce. So think about trees. All right, trees, produce seeds. Those seeds can germinate. Their offspring can grow up and start reproducing while that adult or that parent plant is starting to reproduce. All right, so our equations are going to be based on these classifications: discrete versus continuous, overlapping, non-overlapping. All right, so we're going to start with this discrete, non-overlapping generation, which is annual plants. Annual plants. So our population size at that next interval, the nt sub 1, is going to be determined solely by the reproductive output in our population. All right, it's not going to be affected by anything else. Now, it may seem strange, and you could ask, well, hold on, shouldn't deaths and migrations affect this? Well, no. Migration, we assumed there's no net migration to begin with, so that drops out. And what about deaths? Well, all of our adults die before our offspring start to reproduce. So the number of individuals that die is exactly equal to our starting population size. So that cancels out. So our population in that next time point is going to be determined by how many individuals actually enter our population. And that is B. That's our number of births. All right. Now B, remember, wasn't just our birth rate, like how many offspring are produced per individual. This is just how many individuals enter our population. They're born into our population. All right, so using this knowledge, then, we can try to figure out how many individuals those are by multiplying a birth rate by the number of individuals that are there. And that is the basis of this equation. All right, so the number of individuals that are born into our population is lambda times n sub t. So n sub t is our current population size. So we need to know how many individuals are there and reproducing. And then we have this lambda term, which tells us how many offspring are produced per individual on average. This is the multiplicative growth rate. That's its term. All right, so lambda is our multiplicative growth rate. It's defined as the factor by which the current population size increases or decreases each time period. All right, so that's our mathematical description. More of a layman's term is average number of offspring per individual. All right. So if we just said lambda is equal to 1, that means each individual in our population is going to produce on average 1 offspring. So if we were interested in knowing how many individuals were entering into our population, well, if we start with 100 individuals and each of them produces 1 offspring, then 1 times 100 gives us 100 new individuals entering our population. All right. So based on the description, this discrete non-overlapping generation, this term, this multiplicative growth rate, has also been called the finite rate of growth. So there's like 2 terms that correspond to lambda, and they both mean the same thing. All right. It's the average number of offspring per individual. It's a factor by which our current population size increases or decreases each time period. So if we want to know what's our population size next year, it's this equation. Because we know n sub t plus 1, which is what we're trying to calculate, is b. And b is equal to lambda times n sub t. That's going to be on our next slide, too. Did you get it? Yep. All right. So that's why we're introducing these equations. We want to know what is our population size at a given time point. All right, so our population size next year is simply this equation. N sub t plus 1 equals lambda times n sub t. And as I said at the very end of that slide, it's just how many individuals are born into our population. Because all of our adults die, all of these n sub t individuals die, we only care about those individuals that are born. But that's not really the main thrust of this equation. Usually we're interested in population size after so many generations. So after 10 years, what's our population size? Or after 20 years, what's our population size? And for that, we have a slightly different equation. It's this. All right? N sub t equals lambda t times n sub 0. This equation is going to give us our population size after t time periods. So we have our starting population size, which is this n sub 0. All right? And we know lambda, we know the finite rate of growth. And then we ask, well, in 5 generations, what is our population size? And that's what we're looking at here. All right, so I have an example problem. So we planted 25 marigolds. What are marigolds? Anybody? It's what? It's a flower, right? It's a flower, yeah. Some of you must have done well in botany, right? Yeah, it's a flower, all right? So it's an annual flower, right? So it's going to flower, set seed, and die. All right? So we planted 25 marigolds. Lambda is 1.25 for our seed stock. So the question is, how many plants will we have in 5 years? All right? And what I'm going to do is work through this problem and just kind of show you how we do it. So first thing we want to do is look through the word problem and write down all the information that's in the problem and match it up to our equations. So we want to know our population size after 5 years. All right? So in a problem, we would recognize that marigolds are annual plants. Right? They have discrete generations. So that's going to be our equation that we want to use. All right? So in our problem, I say we start with 25 plants. So n sub 0 is 25. That's our starting population size. I also gave you lambda, the finite rate of growth. And that was 1.25. All right? So 1.25. And then I said, what's our population size after 5 years? And that's our t. So now we just plug it into our equation and solve. So our population size after 5 years is going to be equal to 1.25 raised to the 5th power times our starting population size. All right? And what is that? Let's see if I can get this. It wasn't working the other day. So a black box appeared. Oops, hold on. Disappeared. Where did it go? So I can capture the calculator on here and like actually show it to you on the calculator. but it won't pop up. It's just a black box for me. So that's okay. What we'll do is hide that and let us resize this slightly. All right, here's our calculator. So we got 1.25. We're going to raise it to the 5th power. So it's this x to the y, raising it to the 5th power. And then we're going to multiply by our starting population size. And I got 76.3. Is that what you, those of you that had your calculator? That's what I got. And you can confirm it on your calculator at home. All right? So that's our discrete, non-overlapping generations. All right, discrete, non-overlapping generations. What if we have overlapping generations? Overlapping generations are those individuals that have the possibility where the adults reproduce with their offspring. Now, the reproduction is going to occur basically synchronously or within a very small period of time. So that way you can track the cohorts. These individuals are often presented in life tables. All right, we can have continuous generations also presented in life tables as well. So don't think that just because it's in a life table that it is strictly discrete overlapping, because our continuous overlapping can also be presented as a life table. Our equations are going to be similar for predicting our population size. All right, so these equations is this: n sub t equals r naught raised to the t times n. So just to kind of put it here, we have our second equation, which is basically the same. Only change, instead of lambda, we have r naught. Now what is r naught? That's our net reproductive rate. All right, we're going to learn how to do that in lab. We're going to learn how to calculate r naught from a life table in lab this week. So make sure you bring your computers or tablets. All right, I'll show you how to do stuff in Excel, how to make these tables in Excel. All right, so it's not lambda, it's going to be our net reproductive rate. And this net reproductive rate, if you remember, takes into account both survival and reproduction. All right, so that's a little bit different. Lambda didn't do that. Lambda was all about births. R naught has to include survival too, because some of our individuals can live to reproduce another time. The equation does the same thing. It's going to predict population size in T years, and it's used in exactly the same way. So here's an example problem. We have a cohort life table with 400 antelope in it. All right, for this population, R naught is equal to 0.9. So I ask, what is the population size in 10 years if we start with 400 antelope? All right, so let's kind of go through and work out the problem. Again, we write down what we know. So we start with 400 antelope. I give you R naught, our net reproductive rate of 0.90. And then I ask you, what is our population size in 10 years? Right. What is our population size in 10 years? Do this. Divide that. So that's just plug and chug. Population size in 10 years is equal to 0.9 raised to the 10th power times our starting population size. So we set up our equation, then we can use our calculator. No, still doesn't work. Move that out of the way. So here's our calculator. We have 0.9 raised to the 10th power. Then we're going to multiply that by our starting population size. And we get 139.5. That's our population size. It's after 10 years. It's our predicted population size after 10 years. All right, so it's sometimes you might question whether or not we have a continuous generation or overlapping generation. All right, sometimes you might not know if it's discrete or continuous. Pay attention to the terminology in the problem. If the problem says net reproductive rate, well, you should know that net reproductive rate is R naught. If I say the finite rate of growth, you'll be able to recognize, or you should be able to recognize, that that's lambda. And we only have one equation that has R naught in it. We only have one equation with lambda. So once you have those down, once you know those terms, then it should help you understand which equations to use. This one assumes all of these individuals die, or at least all of your adults die. All right, so this lambda only includes the births. We inherently include births and deaths in this R naught. So it's a good question. I actually have a slide that deals with that. And it's this one. Lambda versus R. So the question was, do we assume that there's no deaths? Well, deaths are kind of inherently built into these equations. All right? Immigration is left out. We assume that there's no net migration. So those terms are just dropped completely. All right? We assume those are zero. If we wanted to include them, we could. We could. But we're not going to, not in this class. Right? So where does deaths come into play? Well, that kind of is what lambda and R naught describe. All right? So mathematically, there's really no difference in these two terms, in the instantaneous growth rate or the net reproductive rate. There's no difference mathematically. It functions the same, and you can see it. It's the exact same equation, it's just a different letter, R naught versus lambda. All right, and both of them are interpreted the same way when we're trying to predict whether or not population grows, declines, or stays the same. So for both lambda and R naught, if it's greater than 1, we have population growth. If it's less than 1, we have population decline. And if it's equal to 1, then we have no change. We have population stasis. And it follows the same idea that we talked about for the life tables. Right? Net reproductive rate was about replacing themselves. And if it's equal to 1, then we have complete replacement. The lambda does the same thing. All of our adults die. If each adult is only expected to have one offspring on average, then that adult is completely replacing themselves. If it's greater than 1, right, we've more than replaced ourselves. So our population will grow. And if it's less than 1, then we have incomplete replacement. Our population declines. The difference between lambda and R naught really comes down to the conceptual meaning of them. What are they actually capturing? Lambda is capturing the increase or decrease in our population due to births only. And it's because all of our adults die every year before the next generation reproduces. So lambda is all about just births. That's all it is. Just births. R naught takes into account both births and deaths. And where does that come up? Well, it came up with the equation of R naught. In our life tables and something that you'll practice, it is R naught is the sum of Lx plus Lx times Bx. So survivorship, which is probability of surviving or probability of dying, and our birth schedule, B sub x. All right, so mathematically they function the same. It's just conceptually, lambda only deals with births, R naught deals with births and deaths. So you might say, well, R naught kind of gives us the average reproductive output. And I'd say, yeah, that's true, but it gives us the average reproductive output if our individuals survive. And it accounts for that. It accounts for that survival. So that's where our births and deaths come into play. Got it? All right, so what does a growth curve look like then? Well, the growth curve for a discrete, non-overlapping generation looks very jagged. It's sawtooth-like. And it's there for a reason. It's because all of our reproduction occurs within a very short period of time. All right, so we have this reproductive period where we get a very rapid increase in population growth, and then we have a steady decline until we get to our next reproductive period. So our overall growth looks like it's sawtoothed. All right, looks sawtoothed. And our peaks, or our jumps, that represents our reproduction. And it has a name. It's called a birth pulse. So our birth pulse occurs, our birth pulse is reproduction in our population that occurs within a very short time period. Could be a week, could be a month, but it's going to be over a very short period of time. So you can see, each generation we have this birth pulse that shoots up and causes an increase in our population. And then between these birth pulses, we have a gradual decline of our population. And this is just due to natural mortality. Because we say that, yeah, all of our adults will die. Some of them will die right after they reproduce, and others will die before they have a chance to reproduce. So this is just kind of like that natural mortality part. Because once we get to this point, we're not saying all these individuals reproduce. We've got some natural mortality, some death that occurs, and only these individuals reproduce down here. All right? So these individuals, some of them will die before they hit reproductive maturity, or they might not reproduce to begin with. All right, so we have our birth pulse, we have our natural mortality that occurs, that's our decrease, the difference between our points. So the difference from here to here, from here to here, from here to here. This difference is our net reproductive rate. And we can look at it as the upper part of this curve, or we can look at it at the lower part, so right before that birth pulse. So from this point to this point, that difference really is our net reproductive rate. This could also be our lambda if we're dealing with annual plans. Now, not all organisms have this discrete reproductive period. Sometimes we're going to have these reproduction periods that can occur more frequently. When we have those periods, what we're going to do is reduce the amount of time that happens before our birth pulse. And if we reduce the amount of time between our birth pulses, what we've done is reduced how many individuals actually die from natural mortality. All right? And if we keep reducing that period, what we end up doing is making these saw teeth smaller and smaller and smaller until we get to a smooth line. So if we change this smooth line and just give it jagged, we can have a very, very fine teeth on it. We see our birth pulse, see the natural mortality. But if it gets to where our time between that is very, very small, then it looks like we have this smooth curve. This smooth curve is when we have continuous generations, where we have reproduction that can occur at any time period throughout a year. So we get to this by basically decreasing that time between reproductive events. This continuous generation, this growth curve, is our exponential growth curve. This is what our exponential growth curve will look like. All right, so with our continuous generations, the time between our reproductive events is negligible. So we don't see that sawtooth, that jagged nature of our growth curves. All right, we're not going to see a birth pulse. We're not going to see mass die-offs, at least natural mass die-offs during our reproductive periods, not like annual plants. All right, our growth curve, thus, is going to be smooth. And it means it's going to be a little bit difficult to identify our change in growth rates, how rapidly it increases. But we can do that. All right, the slope of our curve at any of these time points is going to represent the change in our population size. So I took a spot right here, this point, and what we're interested in is how fast is our population changing at this point. And to find it, what we do is we look at the slope. We look at the slope of our line right at that point. And those of you that have had calculus will probably recognize that the tangent, a straight line that touches our curve at that exact point, whatever that slope of that line is, that's our change in population size. Now we have some mathematical formula for this, all right? Mathematical variables. So our change in population size at this time point is dn over dt. All right, this is the slope at this point. And the dn over dt is kind of related to our delta n. All right, so we introduced delta n. Delta n was our change in population size. Just get this a little bit closer. So our delta n was the change in our population size. And in an earlier slide, we said it was this n sub t plus 1 minus n sub t. All right, so it was one time interval. All right, and that's easy to see because we had discrete generations. We could say from one generation to the next, this is our change in population size. Well, what letter does delta begin with in the English language? D, right? D for delta. There's our D, dn over dt. What this is giving us is the change in our population size for a very small amount of time. All right? So it's still representing our this. It's still representing that for a continuous generation. But this 1 here could be something like this. 0.00001 microsecond. All right? It's at a very specific instant in time because we have the continuous generation. 1 second later, we may have a different population size. And that means we have a different slope of our line, different change in our population size. All right, so this continuous growth is all in reference to this very small change in time period. Our slope of our line is that dn over dt. And it's going to be specific at a specific time point, or for us, it's going to be at a specific population size. All right, so what we see here then, based on this curve, is that the change in our population size is going to be small. We have a shallow slope when we have a small population size. And then we're going to have a steep slope with a large population size. So just looking at this curve and thinking about our slopes, you should then kind of inherently think that, okay, dn over dt must be influenced by our population size itself. And if you're thinking that, you are 100% correct. The change in our population size will be influenced by our population size at that moment that we're interested in calculating it. All right? So our growth in this case is going to be modeled as an instantaneous change. This will be a change at a very, very small time period. It's change at this instant. All right? Our dn over dt is going to be using this equation here. So we've changed, instead of using big B and big D, we're now using small b and small d. So the capital letters refer to the number of individuals that were being born or that died. Our small letters, our lowercase letters, refer to per capita increases and decreases. All right? So these will be like our rates. So what is our per capita birth rate? What is our per capita death rate? That's what this B and D refer to. Now you can say, hold on, what are those? What are per capitas? It's rates. We're going to figure out the rate per, let's say, 1,000 individuals. That's a per capita value. Perhaps it's a rate per 10,000 individuals. For us, it's a rate per individual, usually. So we'll say each individual will, on average, give birth to, say, 0.1 individuals, or 1 individual. All right? These are the death rate. These are per capita birth and death rates. And you can distribute it and say that B times N minus D times N, right? You can get that, and that kind of corresponds to these equations here. But I present it this way because the difference between our per capita birth rate and our per capita death rate gets us this important value R. R has numerous names, 3 that I present here. All right? R is going to be our instantaneous growth rate. It's also called the intrinsic rate of growth. It's also called the Malthusian parameter. This R tells us the potential growth rate of a population based on the difference between our per capita birth rates and death rates. All right? It's going to tell us the potential for our population to grow or decline. Now, why does it take on all these different names? Well, instantaneous growth rate, hopefully it's a growth rate at this very instant. All right? Intrinsic rate of growth, it's at this very instant. This is inherently built into our population. This is our growth rate. What about the Malthusian parameter? Why did it get called that? Any guesses? Any guesses? Named after a guy by the name of Thomas Malthus. Anyone hear of him? Heard of him? He described exponential growth, kind of came up with some of these equations, described population growth using this exponential model. But yeah, Malthusian parameter is this intrinsic rate of growth. All right? So when we calculate this R, we have to do it when our population size is small. And we're talking about right at the very beginning. And the question is why? Why do we need to do that? What's your guess? Why do we measure it when the population size is small? Say what? Okay, so it is practical to count the individuals. That could be some of it. What else? What else? Any of those at home They probably just started it and went back to bed. What do you say? And I know you talked about it in the first year biology classes, because I know I helped a student last year with it. Just happened to be outside my office studying it. Okay, so you mentioned doesn't approach their carrying capacity. So what happens? Why is there a carrying capacity? What do you remember? Yeah, so resources are limited. So we're going to do this. We're introducing this unlimited growth, exponential growth right now, and then our next presentation deals with population regulation. It deals with density-dependent factors that are going to occur. So as our individuals are growing, they're utilizing resources in their environment. You have the effect of competition, all right? You have the effect of internal regulatory mechanisms happening, all right? The development of stress and crowding and all this stuff, all right? If we measured it, or if we try to measure our birth and death rates at a high population size, it's possible that we're actually going to calculate a lower R than what we should be, because that R is being reduced by our density-dependent factors. All right, we're kind of jumping ahead of ourselves, and that's why I kind of put it in blue here to say, hey, this is kind of important. I said this for a reason, and you're going to see it, as you go back and study this, getting ready for our next exam. You're going to be at that point where you can say, okay, yeah, now I understand our density-dependent regulation, our density-independent regulatory mechanisms. Now I know why we need to measure R when our population size is small. All right, so just like our lambda and R naught, we do have relationships. So if our relationships in this case will be centered at 0. All right, so if our intrinsic rate of growth is greater than 0, we have population growth. And we have population growth because that means that our birth rate is going to be greater than our death rate. And these are our per capita rates. So if birth rates exceed our death rates, we get R greater than 0. If our birth rate exactly equals our death rate, R equals 0. It means we have no change. If R is less than 0, then we're going to have population decline. Our birth is less than our deaths. Now, just like these other equations, we can predict our population size, N sub t, using an exponential growth equation. All right? And I think what we'll do is we'll stop here. This will give us a chance to kind of review what R is and then introduce our equations and kind of spend time working through some of these equations on Wednesday. All right. Looking ahead, we're almost done with this presentation. So we're going to do this exponential growth, talk about the assumptions, and then our next presentation deals with when we violate those assumptions, which basically means we have regulation going on. Population regulation. All right, so don't forget, lab this week, bring your computer, your laptops, tablets, whatever. We're going to be doing life tables, a lot of calculations. Be thankful we're not going outside for lab this week. I talked to a former student who remembered the ragweed lab and said, oh yeah, it was horrible. It was rainy, it was cold. That could have been this week. Could have been this week if everything wasn't all jacked up. All right, be thankful for that. Also, don't forget our quiz. So the quiz closes tonight. Make sure you review that last material. The quiz over this will be. It'll be posted. But the thing with our quiz is that I actually have some homework for you to do, and the homework is related to these population growth equations. So it's going to give you more practice. So the quiz over this presentation, I don't think will have you calculating anything. I think it'll just be like your multiple choice, and then there will be a separate part where it gives you practice for these calculations. All right? All right. Have a good one. Try to stay warm.